Hello everybody, this is Michael Walton, Category Manager at Rigel Medical. Today I'm going to do a presentation on electrical safety. We'll do a question answer session at the end of the presentation. Rigel Medical, we manufacture biomedical test equipment from electrical safety analyzers, electrosurgical analyzers, infusion analyzers, defibrillator analyzers, patient simulators. So we've got a full portfolio of test equipment. In today's presentation webinar, I'm going to go over some of it's kind of like a global overview of electrical safety. So that's including Europe, the rest of the world, and North America on various different requirements and some of the standards that's used. The agenda for the day is to discuss or give some insight into the physiological effects of electrical current, demystify the terminology and requirements of the fundamentals, which could be symbols, could be something like +1, +2, what's type B, this type of thing. We'll briefly, well, I say briefly actually, it's pretty much in depth, going various circuit diagrams of what earth leakage is, what touch leakage is, this type of thing. And then at the end of the presentation, I'll go into some of the features of our instrument, the Rigel Medical 288 Plus, which has these nice to have features where it can recognize commonly misunderstood anomalies like secondary earth paths and testing on TN systems. And then we'll show you a quick demonstration of testing a ventilator with the 288 just on the camera. So I'll just go through a quick 62353 automatic test sequence, and I'll show you how to do that with the 288. Right, let's crack on. So, I mean, electrical safety, and some might say clinical engineering and biomedical engineering per se across the board, was born in the 1970s, and there was a great debate about Ralph Nader's shocking, or most shocking exposure, saying that at least 1,200 Americans are electrocuted annually as part of some kind of surgical procedure because of the intercardiac connections with catheterization and use of external pacemakers in open heart surgery. And this was presumed to lead to the potential of ventricular fibrillation, which is a microshock, which we'll go into later. And this guy in the 1970s says, look, wow, this is how many people died in North America, or America in particular. This is scandalous, etc., etc. And this is the reason why I put great debate is because many people have questioned the numbers. Many people, even to this day, have expanded on the numbers. Some say it's 5,000. Whatever it may be, the fact of the matter is, microshock is real, does exist. And I'll go into some of the papers, or at least give some insight into a guy that done some experimental work into microshock and the physiological aspects of current. But it was this exposure that brought to light electrical safety and how it is today. At the end of the day, the outcome of this debate, whether you believe it or not, whether it's folklore within biomedical worlds, the growth of it did come out, or it was at least the birth of a whole new sector within healthcare, and this is the technical support for the healthcare professional, biomed, clinical engineer, clinical scientist. The technical support of medical devices pretty much started then and is what it is today. So whether it was, the overall picture that Ralph displayed in the 70s had some goodness. Some of the electrical parameters, I usually go through these one by one, but I'm going to assume that most biomeds know electronics. So, right, I'm getting somebody saying that you can't hear us, there's no sound. Can anyone hear us? Is that fine? Right, okay. Well, it must be, guys, whoever had no sound, I think it's probably your own sentence, right? Right, anyway. Electrical parameters. So we have, I'd like to think that clinical engineers, biomeds, healthcare professionals know what voltage is, know what current is, etc. They went to college, possibly went to university, they've studied electronics. Well, what is important as far as current is concerned is that current is the flow of an electrical charge, and the movement of electrons are in a conductive circuit. But within a bodily tissue, these electrons carried by ions in electrolytes. So this is why the body is a conductive property. Very, very important, and this is why we'll go into some of the more technical aspects of how you get electric shock. Just because of this, your body is this low-pass filter, but it still carries current. One also thing that I'd like to point out is the capacitance. Because AC voltages are a charge stored and discharged, so AC current will flow. Well, the body is resistive and capacitive, but medical devices have a lot of internal stray capacitance. And we'll go into that, and this is one of the reasons why electrical safety testing in particular is very important. So a guy, Charles Dazeel, did some experimental work, and he categorized the physiological effect of leakage current, or electrical current, I should say, through the body. This was non-invasive by the typical definition of non-invasive. Skin contact, so the skin is the barrier to an electrical source, whether it be current, voltage. In this case, it's current. So he categorized this physiological effect, and he started to increase the current on the person under test. Both men and women were subject to this experiment. He also did some work with different frequencies to see what the effect on the person under the experiment felt. And one point, although there's various different categorizations of physiological effect, the let-go current is pretty much when you've got voluntary control. Anything after that, the body hasn't got control, and then it can lead to ventricular fibrillation and this type. So the let-go current in particular, this one at commercial frequencies, because we're looking at 50, 60 hertz, these are the important Pascal thresholds almost. And a lot of electric safety testing and dielectric strength are there and thereabouts around these points. But what we've got is the increase in frequency means that it takes a lot more current to have the same physiological effect. And this is where things get a little important with low-pass filters and how the body reacts to current. And then we have a thing called microshock. Now, microshock is invasive, and it takes a lot less current to send the heart into ventricular fibrillation than it would non-invasive. This is an important part of electrical safety and understanding physiological effects. So the frequency response of the body is a low-pass filter. From finger to finger, you can probably estimate that it's about 1 kiloohm between fingertip and fingertip, but it's anywhere between 1 to 2 kiloohms. But there's fundamentally between 5 to 1 kilohertz. The let go, the voluntary physiological sensation is flat. right, in this current range. So this is where the body has this flat response, just like a low pass filter would. When the frequency is increased of the electrical current, well, the body becomes less stimulated, so it takes a lot more current to have the same physiological effect. Unfortunately for us, commercial currents are 50 and 60 hertz, so this is where this is the dangerous current that can send the body into ventricular fibrillation of the heart. So why do we need safety testing? The objective is to test for breakdown and damage to confirm that medical equipment is electrically safe to use in healthcare environment. So this is the protection against some microshock, non-invasive and invasive microshock. Depending on what part of the world you're living in, it's a legal liability. But you know, most healthcare organizations would practice electrical safety, and this is protecting this electrical safety is risk mitigation, protecting patients, staff, and visitors. Typically done every 12 months. This is, if you were to evaluate the risk management of the device, it might be 3 months, it might be 6 months, it might be 24 months. All depends on the risk management of the device and what the medical equipment manufacturers stress. Because a lot of when we start talking about planned preventative maintenance, people have clinical governance and guidance and have their own in-house procedures. But various parts of the world do things very differently. Alternative maintenance or alternative equipment maintenance pretty much stress that if you're doing anything, you need to do it in adherence to the manufacturer's recommendation. So you might actually be testing the NFPA 99, but manufacturers saying, no, actually you should be testing that 62353. This is where you need a bit of a extra knowledge between the standards, but also have a suitable device that can actually test to 60601, 62353, and NFPA 99 for those in North America. Anyway, functional current and leakage current. So what is leakage current? Well, functional current powers the device. So if you've got a wattage setting on the medical equipment, let's say it takes 100 milliamps to power the whole system. Well, 100 milliamps might flow through the live or hot conductor, but only 99 might flow through the neutral. So this non-functional current, i.e. leakage current, is escaping the system. What is the analogy? The analogy would be if you've got a hot water system in your household, and you've got your radiators, or you've got your hot water, and you've got a leak somewhere. Well, the only really way to find out where the leak is, because the rest of the functional water, functional flow is within the system, works nice. Oh, the pressure tends to drop a bit. So we've got a drip somewhere, we need to see where this leak is. And that's the similar type of thing, that's what earth leakage is. In reality, in a plumbing system, you might turn the pressure up. That would be dielectric strength in an electric, in the electrical world, to find out where that leak is. So we do a number of tests as per 60601 in the design criteria to try and make sure that we have those creepage levels, and manufacturers in particular of medical equipment have the adherence to make sure we have safe levels in this type of thing. Anyway, if this non-functional current, leakage current, defined by 60601, is within the safe limits of the 60601 design criteria, then everything is good. But leakage currents are due to this stray capacitance and dielectric resistance within medical equipment. So far, let's see if I can draw a picture here. If I have my picture, I can only draw it on there. Can anyone see it drawn there? Yes, right, okay, right. It's I'll just, right, so first time I've used the drone. So just bear with us, guys. So if I've got like, my functional current would flow between live and neutral to, between hot and neutral. And let's say I've got 100 milliamps, right, flowing in this direction, but I've only got 99 here. Well, basically the leakage current is 100, minus 99. And that would be equal to 1. So we've got 1 milliamp escaping the system. How does this escape? It's because of you've got conductors within your, these are conductors that carry current. This would be some kind of isolation barrier. This is our power supply. This is our another isolation barrier, and this is our applied part. Well, if I've got any leakage current, it's due to the straight capacitance, because remember, AC capacitance, apologies, my drawings are terrible. I'm using a mouse. I need to get something a little bit better. Anyway, so this straight capacitance, basically, because I've got conductor current, well, it's just going via these capacitors, and then flowing to the protective earth, and this is where the 1 milliamp ends up. So it's kind of like you've got your conductors, you've got your insulators. By the definition of a conductor and an insulator, you have a capacitor. If I have the scenario where I've got a patient, these are the applied parts, right? He's on a hospital bed, or she, and they're dopey enough or they're stupid enough to go or touch hazardous current source or voltage source, or unfortunate enough, we need to make sure we have an isolation barrier there, because if them touch this electrical source, well, the current will flow through the device and back down to earth, and this guy, he's going to get an electric shock. So what the medical equipment manufacturer needs to provide, especially for BEF and CF type equipment, is we have this isolation barrier. So this is floating. This has no connection to protect the earth. Just something to bear in mind. Let's get rid of those drawings. So in the way that we categorize input protection and output protection and safety is you've got means of operator protection. So the guy or person operating the medical equipment. And then we have the patient. So that would be the means of patient protection. The means of operator protection is to make sure that the operator is free of macro shock and micro shock. And protection is generally on class 1 equipment would be the main protective earth. So you've got to protect the earth from any exposed metalwork, touchable exposed metalwork that's conductor. And any flow current should flow through that earth. With class 2 equipment, we have this box. So these are the two symbols. The square within the square is class 2, and class 2 items can still have exposed metalwork, but they'll have this double isolated barrier, and they'll have proof within the design records that medical equipment is safe because of this doubly insulated barrier. So first of all, when you're doing electrical safety testing, you need to clarify, is it a class 1 or is it a class 2 device? For output protection, we have, basically this is the applied part. What is an applied part? The applied part is the part that is physically in contact with the patient. Can be insulated. The patient connection is the individual point where current flows between the patient and the medical device to do treatment and stuff. But the definition of applied part is it's in physical contact. So there are medical devices out there that don't have applied parts, like for instance, some kind of light treatment doesn't have an applied part, this type of thing. But there's many medical devices that do have an applied part. These are categorized. In this means of patient protection, we have type B. B stands for body, which is non-invasive nerve reference, so something like a hospital bed, for instance. And this is our symbol for B. We have a little symbol there for defibrillator proof. Then we have BF. That stands for the floating, which I tried to describe earlier on in the slide, where you've got this isolation barrier. So you've got body floating, and we have this guy in the box. And then we have CF, which is cardiac, which is invasive, has the floating effect too. And this is a much more stringent level. So the pass-fail thresholds for CF are lower than the pass-fail thresholds for B. So if I'm in a healthcare organization and I want to do electrical safety, there's a number of questions that I need to ask myself. What standard am I testing to? Is it 60601? Is it 62353? Is it NFPA 99? Globally, 3 different standards that's typically used for testing medical equipment. This could be a decision that is in-house. This could be driven from some regulatory agency or authority, or it could be something that you follow within, like I said earlier, an alternative equipment maintenance schedule where you would just follow the guidance of the electrical medical equipment manufacturer. It's also worth considering the visual test, very, very important to determine some of the how good a condition the electrical equipment is. And I'll go into some of the classifications of the visual test later on with 62353. Is it class 1A? Is it class 2? Does it have exposed metalwork, which we need to put our probe on? How many applied parts does it have? And what type of applied part is on the medical device? So you might have multiple. The defibrillator, for instance, has BF and CF, and many devices have a mixture of types. These need to be identified, classified, and you can use a safety analyzer there. Let's say if this in particular would be 3CF. I'm going to the electrical safety analyzer. But many devices are different, and you can select these, the different applied parts for BF and CF on your electrical safety analyzer. Right, I'm going to go into some of the characteristics of the standard and various standards. 60601, mandatory design and type test standard for medical equipment. It's to ensure patient safety and the safety of the user and the safety of the overall environment where the equipment's being used. Came about at the end of the 1970s. And this is worst case scenario testing. So I'm Michael Walton. I've got Michael Walton medical devices. I want to put a device out on the market. I need to make sure that I adhere to this standard. And I want to make sure that the medical device is tested in worst case scenarios and single fault conditions to make sure that when it's out in the field, it has been dropped or mishandled, it's still electrically safe. And we have a body model here, and this is the 60601 body model. Same body model is used for 62353, and there's a variation on NFPA 99. But what we have is an RC circuit that roughly, approximately, represents the body. The flow through the 1K resistor and then the low pass filter. So any frequencies in this range we're not interested in. We're only interested in the flat response of the body and how we measure that current. What fault conditions do we have? Well, we have a number of different fault conditions. We can reverse live and neutral, we can open neutral, and we can open protective earth. And these are various fault conditions that's used within the 60601 standard. We also have mains and applied part, where we put the mains voltage on the applied part here, which is isolated. Then you have some SIP-stop stuff again, but I'm not going to go into the SIP-stop stuff because it's not part of general recurrent test. What tests do you do with 60601? You do an F1 test, and you do a number of these linkage tests to check for this harmful leakage current that we've determined from previous slides. These are in normal conditions and single fault conditions, and the normal and single fault have various different limits on what is acceptable leakage. We have earth leakage, we have touch or enclosure leakages that's commonly known. We have patient leakage, where we measure AC and DC signals. We have patient auxiliary, AC, DC, and then we have the mains and applied part, which is commonly known as F-type, FB in the flow. So we want to prove this isolation barrier. And I'll go through some of the diagrams one by one. So if you were to test, or you were to measure the earth bond or ground bond, as is commonly known in other parts of the world, we need to make sure that we have a really good connection, almost zero resistance from your protective earth to any exposed metal wire. Because if and I'm drawing the picture, let's say this chassis around the medical device is conductive, and we've got a transformer here or some kind of power supply. Let's say this point here hasn't been screwed in properly. It manages to creep over to some exposed metal wire. Well, all of a sudden, you've got all of this current flowing around the device, hopefully going down to the protective earth, and this would take out the breaker. So your protective earth here is vital to be intact. If the protective earth was to go over the circuit, we don't have an earth. Well, the only way current flowing in this type of fault condition, well, let's say it's it's not a short circuit, it's via some of the stray capacitance that we talked about. Well, all the fault current, well, if I'm touching this part of the chassis, or any part of the chassis that's conductive, I'm not going to be touching earth. So any fault current is going to flow through me. So this is why we need to make sure that protective earth is intact, has a really low resistance. And we've got some safe limits within 60601, various limits, different standards. Earth leakage current. What is earth leakage current? We've discussed it many times. But again, if I've got my functional current, which is flowing here to here, this is 100 milliamps flowing in, and I've got 99 here. Well, due to stray capacitance or dielectric resistance, it's escaping this system, and it's flowing through the device, through my protective earth, through my measuring device, which is the body model, back to ground. So that's how we would measure the fault current within the device, and that's what leakage current is. Touch current, as I explained in the previous, the earth bond. If I've got my functional current, 100 milliamps flowing, but there's only 99, and I've got some kind of, stray capacitance or dielectric resistance, then the fault current will flow, through the device to the chassis. And if I'm touching that, because the earth's open here, then this fault current has nowhere to go. So I'm measuring it through the device with the safety analyzer in that scenario. But if I was, touching this and I happen to be earthed, I'm going to get that electric shock. Just going over some diagrams and give you an understanding of what's happening with the various tests. Patient leakage. What's patient leakage? Again, functional current flowing in this direction. Oh, no, it's alternative, but I'll give you the idea at least. because I've already discussed this isolation barrier, what we want to prove is we would make sure that we haven't got any fault currents via capacitance, dielectric resistance that will flow through to the patient. This is where means of patient protection, through our measuring device and a protective valve. If you're a patient there, and you're grounded, well, all of that fault current is going to flow through you to earth. That's why we check for patient leakage. Patient auxiliary, what we're doing here is we've got our functional, any straight capacitance, etc. You get the picture. What we're doing now is we're measuring any current that might flow through between 5 ports. That's what auxiliary leakage does, both AC and DC. F-type leakage is where we put mains and applied ports. So powering the device, it's fair enough, that's your functional current. But what we're doing internally, bearing in mind all of this, this powder blue is this powder blue here is internal to the rifle device, the 2 areas or whatever electrical safety analyzer you're using. What we have here is we have an internal transformer that's isolated, has a single fault condition where we can reverse live and neural. What we're doing is we're putting this voltage on, so any current would flow to the applied port. So we're putting on that, it's 110 of, so if you have 230 volts, that would be 254 volts, there and thereabouts. Apologies for the rubbish drawn. But what we're trying to prove here by putting mains and applied parts is that we have this isolation barrier between there and the protective earth, so that no current should flow. But current does flow because of the nature of conductors and insulators. So we just proven that we have this isolation barrier. So that's the nature of applied port, and that would be the guy or girl on the hospital bed who touches, that hazardous voltage or current. And these are some of the safe limits for your 60601. Looks very complex. There's a lot of information there. Most electrical safety analyzers, like the 288 in particular, you don't need to really. It's nice to have a knowledge to be informed of safe currents, but the 288 in particular, all of these currents, as long as you've identified the device, all of these currents are pre-programmed and will give you a failure if they're above the pass-fail thresholds. One thing that I've started to put in our presentations is, and it's pretty much due to the rapid manufacture of ventilators by manufacturers all over the world. And Rigel have been extremely busy the last month or so. We've been busy because we've had a lot of non-medical manufacturers making ventilators to save people's lives, doing a fabulous job. Biomeds, clinical engineers working extremely hard. I've seen a lot of it on the news and LinkedIn. Really great effort. What they're working hard to try and save people's lives effectively. Well, anyway, in Rigel Medical, we've had a lot of manufacturers getting in touch, and we just need to demystify or at least give people some kind of guidance. Remember, this whole presentation, it's not a directive. We're telling you what to do. Rigel isn't telling you what to do. You kind of come back and say, Michael, you told me you should be doing this. No, this is best practices. This is guidance, but still, we're just giving you what the standards say and the best practice behind electrical safety testing. Not a directive. Must be clear on that. Anyway, people are getting in touch, and we do have a brother or sister company, medical are affiliated with Blair Instruments and Seawood. We have a dielectric strength tester that produces 25 amps, up to 40 amps actually, and has dielectric strength up to 6 kV for DC, 5 kV for AC. And what we're trying to prove is your means of operator protection, your means of patient protection are isolated. So this creepage and this isolation is within the safe recommendations of 60601. So this is within the standard, this is within 60601. More importantly, what's happening here is you put the dielectric strength goes between, let's say this is our earth or ground, and let's say this is our neutral, sorry, live or hot and neutral, and these are going into the actual device here, the plug. But what we're doing is we're live and neutral are shorted together, and we put the voltage, whether it be 1500 volts, between the ground or earth point of your plug between live and neutral. So that's just a little bit of an example of how you go beyond the normal electrical safety test. But this is only pipe testing, stress testing, but that is 60601, not a recurrent safety test. It's not, shouldn't really be part of your preventative maintenance schedule. It's for manufacturers to redeem. 62353. Just, oh, by the way, I didn't really stress that I would be answering all of the questions after the presentation, right? So jot down the questions at any time. I'll get back to them at the end of the presentation. I hope that's clear for everyone. So with 62353, this is the standard that is designed for recurrent testing, is designed for after repair and the preventative maintenance schedule, but still is within the same safety criteria as 60601, i.e. measuring hazardous leakage currents, both the means of patient protection and means of operator protection. Well accepted in parts of Europe. What I have seen, especially in North America, is part of this alternative equipment maintenance schedule. Well, if you were testing the NFPA 99, the manufacturers say, no, we want you to test this to 62353. Typically, if it's being manufactured in Europe, well, you need a safety analyzer to do this, and you need some kind of understanding. And this is why I'm keeping this presentation relatively global. How is it different to 60601? Because we start to look for the objective is to prevent and find potential faults. We have a visual check. We have almost like a sequential order of how you should perform preventative maintenance schedule. And this is typically formed with an electrical safety analyzer and an automatic test, but you can do it manually too and record things. The recording in particular is another thing that is different from 60601, because the traceability is very important with 62353 and analyzing and comparing within 62353. So it's totally different in regards to what it expects the user to do. Also included is a functional check, so it actually measures the current within the device. The visual check, what are we looking for? We're looking for contamination. We're making sure that all of our plugs, leads, any applied part, anything really that has this isolation barrier, this insulation barrier from a conductive part is intact, is not damaged. We're looking at appropriate fuse ratings, because if you have a device that stresses on the back of the device is 1 amp, but you've got a 13-amp cable, let's say it doesn't have internal fuses. You've got a different fuse in the device. Well, fundamentally that's going to be against the design, and that's the wrong type of fuse, and it could lead to a fault condition, and the fuse isn't going to blow up effectively. So the appropriate fuse rating is really important. Safety markings and labeling, so we can clarify how to identify and classify safety testing. The integrity of mechanical parts, so that's making sure that the fit for purpose and for their intended purpose of use. But I mean, all of this visual test really is common sense. 70% of all faults actually are visual test inspection related. Earth bond parameters. We have some different pass-fail thresholds there. I'm not going to go massively in depth, but we do have some different pass-fail thresholds for the earth bond. The earth bond is the same. I'm not going to go through the whole, this is where current flows, etc. I've already been through that. But there is some more definition there, the detached cable and a class 1 device, including power cable. So 60601, that's 200 milliamps. They've increased that for 62353 to 300. Insulation tests, not mandatory. No insulation test is mandatory, even with 60601. But this is a DC test, so we have various voltages, typically 500 volts. So 500 volts would be applied. It's a bit like a DC dielectric strength test. So we have between the applied part, between the connectors here, we short that. We measure the resistance in megaohms by applying 500 volts DC between the protective earth and the live or hot and neutral conductors. And then we have various different permutations of the test. I'm not going to go through them all, but there is not mandatory, does have different pass-fail thresholds depending on what type of test you're doing and depending on the classification of equipment. But this is a DC test. Remember, AC currents, DC currents. A DC test is just that extra dielectric strength test. Electrical manufacturers of medical equipment will typically suggest an insulation test. I've seen that many times in service manuals. So you need an electrical safety analyzer that's flexible and can incorporate different test scenarios. So having an electrical safety analyzer with an insulation test is definitely handy. Otherwise, you're just going to be tripped up with your preventative maintenance schedules. And then we've got the similar classification of our means of operator protection, class 1, class 2, and our means of patient protection with BF and CF. Note B isn't included because we only used really means and applied part with electrical, with the applied part settings in 62353. So what happens if you didn't stress that with the 60601, but let's say we've got our medical device, right? And it's earthed, and it has an applied part. But we know that B applied parts are type B, earth referenced. So if I put mains, so let's say I've got 254 volts here. Well, if that's earth reference, I'm just bang, you're going to have a short circuit. So this is why we don't test mains and applied parts with B type applied part connectors. Anyway, we have different methods of measuring leakage. We so we connect all of the patient connections together. We're measuring the total leakage and we're comparing if we want to do trend and analysis. So this is our equipment leakage for means of operator protection. This is identical, right? I will do some more drawings because I love it. This is our functional current. Any leakage current going through straight capacitors, etc. And it would, what we're seeing now is any leakage currents that might come from the implied parts, or from the chassis, or from isolators, conductive parts, will flow through our measuring device in our Rigel analyzer and back to protective earth. So that's what we're trying to prove with our equipment leakage. That's direct. So that's the direct method, which I've went through. Comparison to 60601 does have the single fault condition of the earth open, and we can reverse live and neural. Only applicable to TN systems, and this is something that I need to stress and go over later. TN systems and measuring earth leakage currents is one of the often misunderstood concepts of electrical safety. We'll discuss that later on. 62353, the differential method. What happens if we have this scenario that I've went over time and time again, where we've got 100 milliamps here, we've got 99 here. Where is this non-functional current flowing through? Well, we don't have the body model anymore, and with the differential method, what we're doing is we're actually measuring by current coil the difference between the current in the live conductor and the current in the neutral conductor or hot conductor. I should stress for all American guys. Anyway, so if we measure this, and this is intact, we don't have the body model anymore. We're just measuring, the straight capacitance for or distance, how it may be coming down. It's a different type of measurement. So we're not doing the Ohm's law. We're not doing it through the body model. It does have some benefits. The benefits are that you're measuring the total equipment leakage. It's impartial to secondary earth connections, which I'll go into later. And we do have an intact ground, so there's no 1K body model impedance or that reactive circuit that I showed earlier on. It does have to have some considerations because of the nature of how it's measured. This measuring circuit here, the accuracy isn't particularly great under certain amounts of current. It can be affected by magnetic fields, and if you have a lot of current, let's say rather than 100 milliamps, so this is 10 amps. Well, if that's 10 amps, then you might have a problem picking up some of the measurements. So that's just something to bear in mind when using the differential method. A frequently asked question is: should I use direct? Should I use differential? Should I use alternative? Some medical equipment manufacturers in the service manuals have various guidance on that. I don't give directives, as I've stressed, but they all have nuances that give solutions that 60601 and the direct method of leakage can overcome. And that is, you can test on secondary earth path systems, stack systems almost, with differential leakage, and you can test on non-TN systems and stack systems using the alternative method. Now, the alternative method, we've got our live neutral, a shorted here, a hot neutral, and we put an isolated voltage between live and neutral to our protective earth. So this is our voltage here, which 230 volts, depending on what part of the world you're in, and we measure it by the measuring device. It's like a really low voltage dielectric strand test, very much what I just discussed earlier on, or an AC insulation test. So what I need to stress really is that it isn't applicable to TN systems, so you can test in surgeries or any floating ground scenarios, but it's not affected by secondary earth paths, so you can use alternative methods to test stack systems. It's current limited because this is an isolated voltage, so the reading is a factored reading or scaled. And the equipment is not powered at any time because we are short and live in Eureka. Right, and then we do have, sorry, this presentation does go on for quite a while, but I'll try and get through it as fast as I can. Then we have applied patient leakage or means of patient protection, AP leakage direct and AP leakage alternative. Direct gets powered, so we're powering the device here, but this is getting the functional current. Alternative isn't, because we're shorting these together, but we are putting the mains and applied part here and here between these contacts, the protective earth and the applied part. So it's fundamentally the same as a mains and applied part full condition as per 60601. We have some different pass fill thresholds for the classifications with class 1 and class 2. We've got alternative methods. We've got the direct and differential. Again, all of these, it's nice to have a familiarity or some understanding to be informed in pass fill thresholds as far as the standards are concerned. But most safety analyzers will do this automatically and bring to the attention that you do have a failure. Right, NFPA 99, common in US hospitals, law in some states. How it differs from previous testing, class 2 equipment, visual inspection only. So you don't test the electrical properties of a class 2 device when testing NFPA 99. There's no real references to B, BF, CF. And there's been various iterations since 2005. So, you have the Joint Commission, and then you've got various agencies and regulatory authorities giving you guidance on how you should do testing. Well, the NFPA 99 has been kind of watered down over the years. So you used to do patient lead to ground, which is pretty much your patient leakage, your mains and applied part, and your patient lead testing. And between leads, you don't do that anymore. All of these tests have been taken out. Chassis and some of the new terminologies with enclosure, touch / chassis, it's now in line with international standards, and we call it touch leakage. And they removed some ground connections as part of the testing, with them being optional in 2015. So it has had iterations over the years. Fixed equipment has its own definition in that fixed equipment is permanently wired. The patient care isn't within the vicinity of this device, and we only do ground leakage at 10 milliamps. Portable equipment is when by definition, you can move from location to location. So there's two different criteria of how you do your testing. Portable equipment is your typical 62353 or there and thereabouts. The body model is different. These characteristics here have a different frequency of response, but it's there and thereabouts, the same as 60601. We do ground bond or earth bond on class 1 equipment only. The limit is much higher. It's half an ohm, 500 milliohms, than 62353. Touch leakage. So again, if I'm going to do nice drawings out of it, if you do have this fault condition, so that earth is open, the fault current will flow through this way, and this is where we pick up. This is the body model effectively. This is how we pick up these, dielectric or capacitance, stray capacitance within the device. One major difference between NFPA 99 and 62353 and 60601 is you do testing in on and off positions of the device, whether that's soft switching or hard switching of the medical equipment. Ground closed is now optional. Ground open is mandatory. Lead ground is your patient tests. It's almost identical to your 606, 60601 patient lead testing, but note that all of the connections are shorted together as per 62353. So it's like a hybrid test. And then these are the limits for NFPA 99, the latest version being NFPA 99 2018. And we have various options for if you want to do ground closed and open, we have different pass-fail thresholds. Again, the 288 or 288 tester has all of these built in and all of this these testing sequences. So although again, it's nice to have a good knowledge and keep informed in leakage currents, most safety analyzers will pick that up. One thing which is different from 62353 and 60601 is extension lead testing and power cord lead testing, looking for some typical, broken pins, the polarity of the actual cord to make sure that the hot went live and the neutral are reversed. Well, the 288 actually has a designated power cord test. We use this is the mains in here, so I guess we go to your mains as your mains plug to go to your main socket. But what this here is for IEC lead testing. So we plug an IEC lead test into the equipment on the test socket on the 288, and that's how we test extension leads, and that's how we test power cords. Extension leads, actually, what you would do is you would have, I'll just draw that again. You would have your IEC lead or power cord lead going into an extension lead, etc. And then, sorry, that would be the other way around here. Now that's the plug going into this, and then you would have one of these plugs going into there, and that's how you can test extension lead for ground continuity or polarity, this type of thing. Also does an insulation test to make sure that it's electrically safe. So that's a feature that people aren't aware of with the 288, which I thought I would put in here. So what's the difference? I've got to stress 60601 design, type test, end of line, crash test dummy, Michael Walton medical devices are going to bring out a device to the market. I must make sure I've dotted my I's and crossed my T's before it's released to the market to make sure it's free of this electrical hazardous leakage current. But if I'm in the world of repair and maintenance, then I do a 62353 test. I don't need to stress test it. I don't need to test it to destruction. I don't need to test it in its worst case scenario. I just do the regulatory planned performance maintenance with either NFPA 99 if you're in North America, or the rest of the world 62353. There is some crossover in the line testing. You can do 62353. Acceptance testing, you can do 62353. But typically people would do 60601 for end of line and acceptance testing. What are the differences, or the main differences? All leakage connections shortened together with NFPA 99 and 62353. 60601, we test them individually, especially CF. Different ground and earth currents and limits, which I've discussed. But for me, I mean, what I've stressed in videos that you can find on YouTube actually is if you're testing the 60601 and you're doing something like an ECG machine, which is a class 1 10 CF device, well, it can take up to 8 minutes or over 8 minutes to test because you're doing over 290 individual tests. If you test the 62353 or NFPA 99, you typically have less than 8 individual tests, so it takes about 40 seconds. So there's a massive time saver in how you do your testing. 62353 pretty much stresses the trending and analysis side. Both NFPA 99 and 62353 stress visual checks. 60601 doesn't. And then the frequency of testing, 62353 typically annually, but again, this would be how you want to be risk averse within your organization, and if you want to follow medical equipment manufacturers' guidance. Right, testing different scenarios. And I'll keep this brief because I know that we are just running slightly over. You can use a 288 to test 3-phase testing. Bear in mind, if you are going to do any 3-phase testing, or fixed, doesn't necessarily need to be 3-phase, it's just fixed. You can remove the earth here, but make sure that you're a competent engineer or you have the facilities or states guide to do this, because you need to be qualified because it's extremely hazardous to remove the earth. And what we do is by removing the earth, any faults, let's say this needs to be powered, by the way. What we can do is any current that comes from any of the phases by the straight capacitance can be the straight capacitance within the medical device. Touch linkage will be the current will flow through the body model, internal, and back to our. And that's how we use the 3-phase testing. So this is powered on, and we can still measure. We don't plug anything into here. Nothing is. We don't have anything plugged in. We have it powered, and we just use this connection and this connection and the applied ports this connection to measure current back there. Hope that makes sense. So that's if you have any more, if you want any more information, just email us and I'll get in touch with 3-phase and fixed testing. But it is possible. Battery powered, the definition of battery powered testing, does it have mains connector, i.e. even a battery charger like a laptop type brick, or does it not? If it doesn't, then it's a battery powered medical device. If it has a charger or it has any kind of AC to DC connector, you have to treat as if it's a class 1 or class 2 device as per 60601 or 62353. But fundamentally, the way that you should do any testing for battery powered devices, if it's purely battery powered, because the capacity of the battery, you don't know what inverters are in these things to produce the amount of power. It could have a really high capacity battery in there. But really what the guidance says and how we do our testing, 62353, you can test it, applied parts testing. 60601, you go from like chassis to chassis. But if you have this in your hands, and this is the medical device, it's pretty much common sense. You're looking at areas of potential. Let's say this is a conductive part here, accessible conductive part. You just want to make sure that from any conductive parts from there to there, there's no the applied part, there's no hazardous current, So that's what we're measuring. We're just measuring as you would with a multimeter almost, point-to-point type of testing on a device to make sure that it's free of hazardous currents. I hope that makes sense. Again, any more questions, just email us after this presentation. And then ultrasound, what we can do is if we immerse all of the probes in this saline solution here, we can put the mains and applied part from one connection and this at 230 would be 254 volts. And then if these, because these are all, this lead is immersed from the applied part. Now this is at mains potential, reference to ground. If I have any cracks or any, because saline is conductive property, if I have any cracks or hairline cracks there, you can't see with a normal eye, and you can't really get a crocodile or alligator clip on or whatever, then I'm not going to be able to test efficiently. So if I put it in saline, the conductive solution will find these cracks, and any fault current will go up the leads down to the mains earth point, which would effectively go back to there, and then we would measure it with the body model internal to the 288, and that's how you would test ultrasound, and that's what the CFD analyzer is doing. And again, any more information on test and ultrasound, please email. TN systems and secondary earth paths. TN system, this comes from the substation. This is our 3 phases. We have phase 1, phase 2, and phase 3. At the substation, these are connected, neural and protective earth connected together. This is only applicable for various parts of the world. They also have 110 volts in many places. But you need at least as far as 60601 is concerned, neutral and earth must be common, because if you have any fault condition, then if these two are separated, there's nowhere back for the current flow. So you're not correctly measuring current. And I'll show you that in the next example. So 60601, the standard specifies that you must do all of your testing on the TN system. But remember, well, actually, it's the same with NFPA 99 because it uses the same type of measurement. 62353 does have solutions to test on TN systems like the alternative method. However, to correctly measure your leakage currents, you really must be on a TN system. Why? Because if I've got the current flowing through here, right? Because protective neutral, common, if I've got 230 volts from live and neutral, I also have 230 volts between live and earth. I've got 230 volts here. So after, let's say this resistor is our medical device. This has got a fault current. This would be a failure. All the current would flow through the resistor, the medical device, the protective earth from the live conductor. If I have a IT system, a non-TN system, well, the voltage between live and neutral would be mains voltage, but the voltage between live and earth could be, and these are arbitrary figures, but it could be 100 volts less, because this is flowing. This isn't connected anymore, so we don't know what this voltage means. So this current, it could be anywhere, but it's going to be less. Therefore, if you test on a non-TN system, your fault current is going to be less than the real fault current. And this is why it's integral to get an understanding of what TN system is. The Rigel gives you a message. The Rigel 288 will tell you if you're on an IT system, and it will tell you of this isolated earth. It's a real good indicator to make sure that you test the medical devices correctly. Another message that we get is a secondary earth path. Now I'm going to go into that now. What is a secondary earth path? Well, if you want to measure current effectively, if this was touch leakage, or earth leakage, and I wanted to show you how the fault current works. So this is my device, and internally I have this body model. I'm just going to draw it as a resistor. So any fault current will, be in this circuit path from the test lead, comes via the test lead, right? But if I have another device that's connected and flown down this path here because of an auxiliary device, all of the fault current will flow through, and I've got an arbitrary figure there of 1 ohm. So a measuring device, which is a 1K resistor that's internal here to measure the current, won't measure anything, or it will measure something that is going to be deemed as safe. So if you haven't got an electrical safety analyzer, it isn't informing you of these alternative earth paths or secondary earth paths, then you're not correctly measuring the fault currents. Commonly misunderstood concepts of electrical safety testing. And last but not least, I know we have went over. I am going to go to the demo, so stay tuned. So, as people would probably say, when we do earth bonding, protective earth is giving us that protective integrity from touchable parts. We've stressed that if any of these, if the conductive part was to become live or hazardous, it's given us primary form of protection for class 1 equipment. Then hopefully it will trip the fuse or the circuit breaker. But different standards have different currents and different pass-fail thresholds. But what are we measuring? We are measuring low resistance ohms. Is it possible to combine the benefits of the different currents? Well, yes, it is. We have the Rigel electrical safety analyzer. So on the electrical safety analyzer, that will give you this kind of, it gives you a spike of current. It's a low current because that's the nature of measuring, or safely measuring low resistance values to make sure that you have that mechanical connection in place. It's a real solid mechanical connection, so you haven't, when you've been screwing the device back together, the earth, if you're using a low current, you can pretty much identify if you have a really poor mechanical joint. And that's why we use low current. But we do have a high current. This high current zap circuit, we call it, breaks down any film resistance or minor oxidization buildup like dust, like grease. So the low current after the clean contacts is the most accurate way to show quality of the contact of the bonding and the mechanical bonding. But this spike here will just do any breakdown of this constriction resistance due to aging contacts. So we have that in our device. It is the end, well, kind of the end, nearly the end, thankfully, because it is a long presentation. But if you do want any information, we do have a really in-depth guide on practical, the practical guide to 60601 and 62353. You can download them from our website at any time or get in contact with us via email. Please follow us on Facebook, on LinkedIn. We do a number of videos on YouTube, and we use Twitter too. So all the social media, I'm really active on LinkedIn. I put a lot of stuff out there. I write articles. I give people information. Our Rigel mental page too. So it's good to follow and just keep connected. This is our address in the UK because that's where all the manufacturing is. What we do, again, I'll stress this, we have the calibration services all over the world. That's 17125 calibration services in India, in Singapore. We also have an office in KL, in Kuala Lumpur, Malaysia, and we have an office in Tampa, Florida, and a service center in Florida. So we've got worldwide coverage of buying and servicing our medical devices. Right, okay. I'll get to the questions after I've done the demonstration. Just bear with us 2 seconds. Right, this is our 288. And over here is our medical device, which happens to be a ventilator. It's 1BF, so I'm going to set this up as a 1BF. I've already got, if I just expand this, I've got my alligator or crocodile clip going to an exposed metalwork, so I've already preset this up. And then I have the device under test plugged in to my safety analyzer. I have the applied parts here, which is this thing connected to my applied part 1. And I'm going to set this up to do an automatic testing. It's very, very easy. So what I'll do is I'll press F4, press auto mode. If it has an asset ID, I'll put that in. For the purpose of this exercise, I'll just put anything in. This is not important. I'm going to select the class. I'm going to use 62353. It's a class 1 device, and I'm going to use direct because that's pretty much the commonly used test for class 1 62353 testing, very similar to 60601. I want to put this down as automatic. The run mode, automatic and semi-automatic, which you can see there, are used because you have to test leakages in normal use, in inverted commas. Sometimes we need to power the device and leave the device powered before it'll run the operating system, and the device is being powered. So we give people options on how they prefer to test or measure leakage current by doing that. Then we have our testing period. I'm going to just keep that as default 12. But we have to press F1 because we want to determine our classification. And I've got, it's type BF, and I'm going to have 1 applied part, 1 patient connection. That'll be highlighted here. If I'm testing something like a defib, I can select CF, BF on different applied parts within this menu structure. So I'm quite happy with that. I'm just going to press F4. And then I've got a number of characteristics I can put in there. I can put in for traceability purposes, the site, location, make, model, description, serial number, this type of thing. I'm just going to leave this as default just for the purposes of this exercise. And then it's going to give us some on-screen advice. I've already got my crocodile clip connected to the exposed metalwork, but it does prompt me to do that. And then I'm just going to press start, and then it's going to measure the low resistance of my earth bond, and then it's going to start to power the device. When it does power the device, it's going to ask us to turn the device on. So what I'm going to do is I'm going to turn the device on, and then I'm going to press start, and then we'll go through and do the 62353 dielectric test sequence. BF. Note that the fault conditions, or at least the live and neutral reverse to show on the screen, and that at the end of the test. I'm quite happy with that. Now I'm going to save that test. And all of those test results are saved within the tester. I'm just going to turn that medical device off. It's really annoying. And that is the end of the demonstration. So it's something very quick. So with the end of the demonstration, I will answer some questions. I noticed that we've got a number of questions here, and I'll work through them one by one. Can I get a certificate of attendance? You can get a certificate of attendance. We don't have any accreditation at the moment. Our product management team, our application team are grown. We're going to be doing a lot of videos, etc. But we're also going to be putting out some continual personal development accreditation programs where you will get a credit for watching the presentation. But this, we were putting things together, and then the coronavirus happened. So that's one for the future, but it is definitely gonna happen. Can I find your webinar online? We will be posting videos of this presentation online. Yes. So you'll get an email more than likely from our marketing team. Is the presentation going to be available afterwards? Yes. We'll send on a PDF of that, of the presentation. Can I use a digital multimeter as a body model? No. You've got to use a specialist device like an electrical safety analyzer, like the 288. How often do you have to calibrate test equipment? We recommend every 12 months, so annually. Just got a couple more through here to work through. There must have been some distortion on that audio. I'm not really sure why that is. When testing a class 2 device, should I connect earth or the earth cable to the device? Although the device case is plastic and there is no metal spot to connect. So basically this guy is saying he's got a class 2 device. It's all in plastic. How do I correctly test to a standard if there isn't any exposed metalwork? Well, I've got a really boring answer, but it is the answer, and it's what in adherence to the standards. Basically, if it is totally insulated, you would use some kind of tin foil, and this tin foil would give you that overall exposure to any cracks or anything where there could be a potential fault. Sounds very futile, possibly the reason why NFPA 99 don't test class 2 devices, but still there is a solution out there, and that's the guidance that we give. How do you test if the come-in supply live and neutral is reversed? Well, if live and neutral are reversed, the 288 will actually turn the polarity around automatically. So it doesn't really matter if you have live and neutral reversed in your supply. So the 288 recognizes that and will rectify it before it does any testing. How do you test class 3 equipment? Well, Sharif, you mustn't have been listening earlier on because I went through that with class 3 hasn't got a definition. So a battery powered device in portable appliance testing and general electrical safety of electrical equipment. If it was, some countries do portable appliance testing. And the definition of class 3 is almost like a cell. It's like the low voltage. I can't remember. I think it's below 48 volts, but don't quote us on that. Anyway, in 62353, in NFPA 99 and 60601, class 3 is not recognized. So if it is a low powered device, i.e. uses a battery charger, if it uses a battery charger or laptop type brick charger, AC to AC, AC to DC, you have to test the medical device as a class 1 or class 2 device. If it is a battery powered device only, there's methods of testing that device. Please email us or watch the presentation again when I was discussing the battery powered device. Can I disconnect the earth connection? Right, okay. I think there's a little bit of a misunderstanding there, Onwa. in that I'm not quite sure what you mean by disconnect the earth test for the crocodile connector during the EUT test after the resistor has been checked. I don't know what you mean, sorry. You need to make a little bit more sense of that. Do you have to send calibration device to your office in the USA? We have, so, okay, globally, we have global representation pretty much everywhere. We've got distributors in the US. If you buy the instrument in the US, we have an office there, so we have full after-sales support, and that's including calibration. We also have calibration partners within various states in the US and in Mexico. So just fire over an email and we'll be able to help you out on any of that guidance. How do you test three-phase equipment? I've done that in the presentation. Just watch the presentation again or email us. I'm not going to go over that again, sorry. Is it wrong to test medical equipment using 60601 standard during a preventative maintenance schedule? No, it's not wrong. Remember, I'm not giving a directive. I'm just giving best practices. Many people still use 60601, but 60601 is type test and 62353 and NFPA 99 is scheduled recurrent after repair testing. So that's the definition, that's the best practice, but it's however your organization or the clinical governance deem fit for risk mitigation, what standard you use. If the test is started, should it be connected to the wall during, right, is this going back to, again, you would have to be clear on that question. Just send us an email in the email address to support and I'll be able to clarify and we won't get bogged down with this misunderstanding of because I don't really understand the question. How do you use a test to differentiate between three-phase lines? Well, you don't, because it's the summation of current, because we don't need to test between we don't need to test between phases for the fundamental of electrical safety, because we're trying to make sure that this thing is free of hazardous voltages and hazardous currents to human beings. So if the in phase, if the outer phase and you've got this, many different phases, we're still looking at RMS current, so it doesn't really matter. What would happen in a power surge? Is it going to break medical equipment? Not if it's on a surge protector. But this has nothing to do with electrical safety. Anyway, has anyone got any more questions? Take that as a no. Therefore, if you do have any more, I do have the email address here. It's been a really good presentation for me personally. I've enjoyed the interaction. I've enjoyed answering the questions. It's a bank holiday weekend here. It's 7:30 at night. I'm going to grab myself a beer. I'm going to go home, and then I'm going to relax the rest of the weekend, and then come back to work on the Monday. We are in lockdown in the UK with the coronavirus. We're hopefully will be up and running very soon, but we're still manufacturing. We're just on a limited staff level, but on Monday everything should be back to normal within the safe requirements of social distancing and working within the social distancing criteria. Stay safe, everybody. Have a good weekend. Any more questions, fire them over. Thank you, everybody. Bye.